Okay, so what we've been talking about the last couple of lectures is the idea of filtering. So we introduced beginning, I think it was last Monday, the idea of filtering and basically kind of outline this sort of four-step process. So if we have a system and a system meaning, you know, a circuit like what I have here, all right, which I'm going to look at a little bit more detail here in a second. But if I have a circuit like what I have here, so there's an input, in this case, I got a voltage source input and I got a voltage source output, or a voltage output across this resistor. What we're saying is when we kind of apply this filtering concept, what we do is we sort of determine the Fourier transform of the input. Now I keep everything in this context of X of t is my input and Y of t is my output. All right. So in the circuit that I have over here, where I have my input is a voltage. So X of t is Vn of t. That's my input. And Y of t is V out of t. All right. So those are my input and output as I define them in this particular example. Okay. All right. So what we do is we say, okay, well, if I know what my input is, I can determine the Fourier transform of the input. I can figure out this thing we call the transfer function that relates the input Fourier transform to the output Fourier transform. And we worked out this relationship here, right? So basically what we say is the Fourier transform of the input times the transfer function is the Fourier transform of the output. What we can then do is take that Fourier transform of the output and convert that back to our time domain signal. Now, you've been using this all the time in circuits 2, all right? In circuits 2, what you did is you take, I don't know, you could have had this, this particular circuit right here. And what you may have said with Yahoo is you might have said, well, this is 3 cosine 2t. And you need to figure out what you guys do there is you convert this to a phasor. So you say this is 3 angle 0. Well, this is a Fourier transform, all right? Because what that is, if I look at that 3 angle 0, right? If I look at this here, how does that relate to the Fourier transform? So I say it's 3 e to the j 0 degrees. How's that related to the Fourier transform? What is this here? How's that relating to the Fourier transform, this phasor thing? It seems a lot simpler. We don't talk about the mathematical details as much in circuits 2, right? We just kind of leave it to the fact that, okay, well, I can pull out the magnitude and the angle and just kind of track what happens to them through the circuit. But this relates carefully to the Fourier transform because in the Fourier transform, all I do is I would have replaced this and say, well, the Fourier transform of 3 cosine 2t would be 3 over 2 e to the j 0 degrees located at -2 and 3 over 2 e to the j 0 degrees at 2 radian per second. Basically what we do is we just end up taking this coefficient and we apply that. This thing here, 2 times that is what we call the phasor. All right, so we're basically just doing a little bit more mathematical rigor around the stuff that you're used to doing in circuits 2. Does that make some sense?
Yes.
Okay. All right, good. Yeah, that's the basic sort of concept, right? Now, the reason we have to use this is if I have an input like what I have right here, this guy here is a square wave, right? So if my real input is a square wave and not something simple, right? Yahoo keeps it simple in the context of, all right, so we had sinusoidal inputs only. All right, if I don't have sinusoidal inputs only, if I have something like this square wave that I have shown here on the left, that square wave is still a sum of sine waves, okay? And what we're saying is I can compute the Fourier transform of this thing and basically apply the transfer function concept at each of the individual harmonics, basically computing the phasor of each individual harmonic. That's really what you're doing, is you're computing the phasor of each individual harmonic that's in that square wave. And then basically saying, well, what's the phasor of the output at that frequency? and then you're converting that back into a time domain waveform. Okay, so it should make some sense as to what we're kind of doing there. All right, so last time what I did was I went through an example. If you watch that video, basically it's I have V in and I have this LCR circuit, and I went through each of those 4 steps. So, and I did it with 2 cases, right? So in one case, I had L is 10 henries, C is 10 farads, R is 1 ohm. And the other case, I had a much smaller L and C value, okay? So I went through this process, basically walking through these 4 steps. So the first thing I did was to figure out the Fourier transform of that input waveform. So if I want to figure out the Fourier transform of this waveform, how do I do that? I just want to make sure people have an understanding of how to do that. How do I figure out the Fourier transform of that V n of t here, this square wave? What would be my process? Because that is a good test question.
Getting the alpha ends through the integral.
Yep. So I would get my alpha n's, and then I map those alpha n values to the frequency domain, right? So the process basically, if you go back to the video, it's basically like this, right? So I basically say, because this waveform is periodic, I can, use the definition of the alpha n's to calculate those values. And what I ended up with last time was this. Okay, for this particular square wave, this is what I get. And I always do separately the value of alpha 0, which is the average value of the waveform, right? Which is just the area under the curve, which in this case is just simply 2.5. All right. Now that I have that, so I have the alpha n values. These are what I would call the Fourier series coefficients, because they are the coefficients in the summation. In this case, V n of t is the summation from n equal negative infinity to positive infinity, alpha n e to the j n omega naught t, like that. So we call them the Fourier series coefficients because they're the coefficients on these exponentials, right? And again, just to remind ourselves, that just basically means that this thing is a DC value, which is constant, plus the other way to think about this is as a bunch of cosines. What's the difference if I go to the cosine form of the series? What's the summation? What's the range of the summation? Is it negative infinity to positive infinity? What is it then?
0 to infinity.
Well, it's 1 to infinity.
Yeah, 1.
And we add the DC term outside of it, right? So in this case, instead of putting it, usually that's where we usually use the C term, but I'm just going to basically say it's 2 times the magnitude of alpha n cosine n omega naught t plus the angle of alpha n, right? I can relate those 2 things together. It's a little bit easier to think of it in terms of cosines than it is to maybe think of it in terms of complex exponentials, but that's the basic concept, okay? So we're saying this guy is made up of a bunch of those cosines. So now once I have the alpha n values, how do I go from the alpha n values, the Fourier series coefficients? How do I go to the Fourier transform? So the alpha n basically are just numbers. They're complex numbers and they're associated with individual harmonics, right? My V n of t is a waveform that exists in the time domain. In other words, I could stick an oscilloscope probe onto a voltage source and the oscilloscope would tell me what V n of t looks like. When I have the Fourier transform, I plot the Fourier transform on a set of axes. When I plot the Fourier transform, what's the x-axis? What's that x-axis on my Fourier transform? Nobody knows?
Omega.
Omega, that's right. Yeah, so basically what I do is I plot a series of impulses. So we basically, the relationship here is my Fourier transform expression. Basically what we're saying is and this is important to remember, like the original waveform Vn of t is in the time domain. Its Fourier transform Vn of omega is in the frequency domain. What that means is when I plot Vn of t, I plot it with a time axis as my x-axis. Vn of omega, I plot with frequency on the x-axis, okay? And because these coefficients, because they are complex, I have to make two graphs, right? One graph is of the magnitude and the other graph is of the angle, okay? And what we say is we expand this thing and it's a series of impulses. So what it's telling me is if I were to look at this and just look at the magnitude for a second right here, okay? What I've done here is I listed out the individual, I've labeled, I guess, what the individual impulses are, okay? So when I see something located in the frequency domain at omega equal to 0, what's the meaning of the amplitude of this impulse? What's it mean to say that this at omega equal to 0, this thing has a magnitude of 2.5? What does that mean about the waveform in the real world?
DC term.
That would be the DC term, right?
Yeah, so that's right. So that means that the waveform has a 2.5 volt DC term. If I wanted to figure out what does it mean then, this alpha 1 and alpha minus 1? What about those two things? What do they tell me? In this case, they're about 1.5. They're not quite 1.5, but they look like they're about 1.5. What does it mean if I have two impulses there that are both have a height of 1.5? What does that mean about the time domain? So one impulse is located at omega naught. The other one's located at negative omega naught. What does that mean? What do they tell me? If I see something like that, if I see a graph that has something like that, what does that tell me about what exists in the time domain at that frequency?
It's a cosine function.
It's a cosine function, right? So it'd be 2 times the magnitude of alpha 1 times the corresponding cosine would be whatever this would basically be, this expression down here at the bottom, right? I could look at those impulses and say, if I have an impulse located at omega naught, then I have a cosine with a frequency of omega naught, and I could go to here to figure out what its angle is. So its angle in this particular case looks like what I have is 2 times the magnitude. The magnitude is about 1.5. It's not exactly 1.5 if I look here closely, but I'm just going to round it to 1.5. And omega naught in this case is just 1 radian per second. What's it look like the angle is here for this guy? What's it look like the angle is in this particular case? At omega naught equal to 1. What's it look like that angle is?
Looks like about negative 90 degrees.
That's right, it is, which means that this guy is basically a sine function, right? It's basically sine of t. So what it tells me, and I could keep doing this for all of the other harmonics. In this case, the second harmonic is 0. The third harmonic has some value. The fourth harmonic is 0. Fifth harmonic has some value, and I could keep going along like this, right? The important thing is you guys should know how to be able to make those relationships. All right. Now back to this kind of filtering idea. Right. So what I just did was figure out the Fourier transform of the input. So if I want to figure out the transfer function, effectively what I need to do is to go back and look at how I can get this from the circuit, right? So I can look at the differential equation, and I went through this. I'm not going to go through this now. If you want to go back, look at the video that was posted for last Wednesday, and it'll walk you through how to go from the differential equation to the actual transfer function. The important thing is in the differential equation, everywhere where I have a derivative, I end up replacing that derivative with a j omega. And if I have a second derivative, I replace it with a j omega squared. If I had a third derivative, I'd replace it with a j omega cubed. Now, if you look at this, the result that you're going to get, at the end of the day, what I get is this relationship here, right? So once I go through this whole bit of math, I get that V out of omega, the Fourier transform of the output, is equal to the transfer function, this whole thing, is equal to the transfer function h of omega, right? Transfer function h of omega times the Fourier transform of the input is equal to the Fourier transform of the output. This h of omega, how else could I have gotten h of omega? So I walked through this whole thing about, okay, I get a differential equation from the circuit, and I can convert that differential equation into a transfer function. How else could I have gotten h of omega here? What other approach would have worked that you know from circuits too?
Voltage division.
Yeah, basically this is, impedance analysis is a direct result of this, right? The fact that if I have, on a capacitor, I equals C dV dt, right? Basically, if I take the Fourier transform of this, it says I of omega is equal to j omega times C times V of omega. So if I look at that, V of omega is equal to 1 over j omega C times I of omega. Right? 1 over j omega C is the impedance of the capacitor. So impedance analysis is really kind of a special case of this whole sort of analytical approach. So what we're being asked to do, right? Once we know what the transfer function is, so once we know what h of omega is, basically what we do is we say, all right, I need to calculate what the Fourier transform of the output is going to be by plugging in the frequencies at which I have something going on in my signal. And that's going to give me basically this result down here at the bottom. It's going to give me how V out of omega relates to V in of omega. All right, so let's look at sort of the way we approach this. This is what I had last time, and I wanted to go into a little bit more details about this because I tried to do it kind of an introductory sort of way the other day. So we say is V out of omega is equal to V in of omega times h of omega, right? That's kind of the key result. And you have this in problem 3 and problem 4 in the homework. Now, what I've done here in this graph on the left is I've shown both the magnitude and the angle of V in of omega. So the Fourier transforms the input. And then I also plotted on top of it h of omega, which is the transfer function. All right, so we found for this particular problem that h of omega is equal to 1 over j omega squared LC plus, what is it, L over R times j omega plus 1. All right, we found that. Now, the thing is, this thing is basically, I can think of it like this. It is a complex number. And so I can write it like that. It basically has a magnitude that is a function of frequency and an angle that is a function of frequency. And what I've done on the top graph is I've shown what that magnitude looks like. And on the bottom graph, I've shown what the angle looks like. Now, when I look at this, I've talked about this idea of, so what this is doing is this is filtering. So what does it mean to filter? What it means to filter is to get rid of certain signals. So when I look at this waveform, or this particular h of omega right here, what type of filter would this be? Does this look like it's keeping low frequencies or keeping high frequencies? What do you make of this? Looking at this magnitude of h of omega, what does it mean? This magnitude of h of omega, it's close to 1 when omega is equal to 0. And then as omega gets higher, the magnitude drops way down. So what's that mean about high frequencies here?
It's cutting the high frequencies. It's a low pass.
Yeah, it's reducing the magnitude of the high frequencies, because basically what I'm going to have is this is our basic relationship here. So if I want to figure out, I can use this at any given frequency to figure out, okay, well, at the 10th harmonic, right? So V out of 10 omega naught is equal to whatever the magnitude of H is at 10 omega naught times whatever V in is at 10 omega naught. And because this guy is getting smaller as frequency goes up, it would appear from looking at this graph that the magnitude of H as I get to a pretty high number is going to be getting pretty close to 0. Okay. So that tells me that high frequencies are getting reduced. Now, the thing that's tricky here is what's the meaning of a high frequency and what's the meaning of a low frequency? That all depends on the values of the L's, the R's, and the C's in the circuit. And we're not talking about that right now. What we're talking about is just the basic concept of, is this a low pass filter or is this a high pass filter? This is what I would call a low pass filter because it's passing low frequencies and getting rid of high frequencies. In other words, the magnitude of H is getting so small that the Fourier transform coefficients are going to be very small at those high frequencies. Okay. So looking at this, I mean, if you just looked at this picture right here visually, what frequencies look like they're successfully making it through that filter? In other words, which frequencies look like they're not being zeroed out? What do I mean by being zeroed out? Because what am I saying? Basically, so this relationship here, the V out of omega is equal to V in of omega times H of omega. What's that mean about the magnitudes? Well, that means that the magnitude of V out. So first of all, if I just have this, if V out of omega equals V in of omega times H of omega, those are complex numbers, right? So the magnitude of V out would be equal to what? If I have this relationship here, V out equals V in times H, what do we know about the magnitudes of all three of those? How do the magnitudes relate at any given frequency?
The magnitudes are the same.
Well, at any given frequency, they're not necessarily the same, right? What you'd say is that, okay, V, because this is complex and I've got complex numbers multiplying each other, I'd say V out of omega magnitude is equal to V in of omega times H of omega magnitude. In other words, their magnitudes multiply each other, right? So at low frequencies, my magnitude of H is approximately 1. And as I get to higher frequencies, the magnitude of H is approximately 0. So to figure out the magnitude of the output at any given frequency, I just multiply those two magnitudes together. So what does that mean then in terms of this picture right here, without doing any math at all, just looking at this visually, what do you expect the magnitude of V out of omega? What do you expect the magnitude to be at something like here at omega equal to 3? Or at omega equal to 5, or omega equal to 7? What do you expect the magnitude of the output to be at those frequencies? What should that be? Just based on this picture. What's it look like the magnitude of H is right here at this point?
Just about 0.
About 0. That means that the magnitude of the output should just about be 0 as well, right? Because so I'm basically taking, a number close to 0 times whatever this value is, right? And a number close to 0 times whatever this value is. So I'm attenuating or reducing the size of those coefficients at those frequencies. All right. Physically, that's because of what the capacitor and the inductor are doing, right? So if I want to figure out V out of omega specifically, right? What I'm doing here is I say, all right, let's just think about the magnitudes, because that's a lot easier to think about. I say that, okay, the magnitude of V out of omega is equal to the magnitude of H of omega times the magnitude of V in of omega. And I can apply that at every frequency where there's actually an impulse. So what I know about V in of omega is, we defined it as basically it's this series of impulses, right? It's this series of impulses like this, omega minus n omega naught. So what that means then for the output is it means that V out of omega is, because it's H of omega times V in of omega, it's basically going to be this. It's also going to be a series of impulses. The only difference is I'm going to take the alpha n values and I'm going to multiply them by the value of H at that particular frequency. So in other words, there's going to be impulses at all the same frequencies, okay? Because there's sine waves at all the same frequencies. It's just this transfer function is telling me what that magnitude is going to be. So the question that I have is, okay, well, how would I code this? How would I get this expression into code to figure out what the magnitude of the output Fourier transform is going to be? Because that's what I'm asking you to do in problems 3 and problems 4 in the homework. How would I code this? What would be the way to approach it?
For loop of getting the alphas and then multiplying that by the h's, like have a vector for h and vector for alpha and multiplying them together.
Yep, that's right. Yeah, totally. So what I did here, again, I did this just for 7 harmonics, but basically I calculated what the alpha n values are, right? So you can go back to my expressions and see that that's the expression I had for alpha n. And what this alpha n is basically going to be a vector that contains 15 entries, right? Because I did this for 7 harmonics. So I'm saying 15 entries because I'm going from -7 to 7. So that's 14 sine waves plus the DC term. Okay. So it's 15 terms in total. So basically what I define then is this guy here is my Fourier transform of Vn. Right. So whatever the alpha n vector is and Vn are the same thing. In other words, this is the Fourier transform of Vn of t. Okay. Then what I do here is I got this for loop where I placed in here what my transfer function is. So I had that H of omega was 1 over j omega squared LC plus j omega L over R plus 1. So what I did was I went through this for loop and I defined for myself what omega was. Okay, so it's n times omega naught. So basically, so what I'm calling here, right? That's my omega. I'm basically saying for the given harmonic, it's n times omega naught, right? And then I'm plugging that into H, and then I'm multiplying to figure out what the value of the Fourier transform is going to be at that particular point. Okay, if I looked at this, how big is H going to be? What would H look like? Based on the way this code is set up, is H a vector or is it just a scalar?
Vector.
No, it's just a
Okay.
scalar, right? Because what I'm doing is so n of k is a number, right? So omega naught is the fundamental frequency. So this is basically one of my harmonic frequencies, and I'm calculating the value of H at that frequency, and then I'm calculating the value of the output Fourier transform at that frequency. Make sense?
Yeah.
Okay. So with that, what is that going to look like? So if I were to go through and to do that, so I plotted for just the magnitudes here. Now, basically what we're saying is that V out of omega looks a heck of a lot like Vn of omega. So Vn of omega, if I write that out as well, Vn of omega is a series of impulses from negative infinity to infinity. Right? The only difference here is that those impulses are now multiplied by whatever h is at the same frequency. So what I did is I drew a graph of the magnitude. All right. And then what I also wrote out here was essentially what the magnitude is, so we can kind of see the numbers. Because when I look at this, it really looks like only the first, I can only see the DC term right here. But what I did was I just kind of zoomed in so I could see for the output that they're pretty close to zero. All right, but not exactly zero, pretty close to zero. So I wrote this out here. This is the n equal to 0 or omega equal to 0. This is the n equal to 1 or omega equal to, in this case, omega naught, which is also 1 radian per second, just because of the example. This is the n equal 2. So this corresponds to 2 omega naught. This is the n equal 3 or the 3 omega naught. Right. So these information, this tells me how big the corresponding signals are in the time domain at the output. So basically, I just wanted to be able to see this and see that, okay, it looks like the values are going to be like, when I look at the h of omega, well, it looks like it's almost 0 out here. So it looks like the output's going to be almost 0, and it is, right? It's not quite 0, but it's almost 0. This is telling me that according to this, it looks like the magnitude of V out at omega naught is basically about 0.016 delta of omega minus omega naught, like that, right? So his magnitude is awfully small. Not 0, but very small. So if I think about this, I had a square wave, which was 0 to 5 volts. And now what I'm saying is this value here is 0.016 volts. So the amplitude of whatever I have in the output at omega naught is going to be much, much smaller than whatever I had in the input. Okay. So what I want to do is then I want to say, okay, well, let's think about what V out's going to look like. So what I did here was I wrote out, again, this is what the magnitude of V out is, and this is what the angle of V out is. Now notice what I did here as I put a little tick mark there. What's that tick mark doing? Anybody remember?
It's transpose.
It transposes, yeah, because my V out was a row vector. It was a little bit easier to visualize it if I made it a column vector, right? So the middle term, right, on both sides, this is the n equals 0 term, right here and right here. Okay. Then I have an n equal 1 term and an n equal to -1 term. So I want to focus on those two. So if I want to think about constructing this thing, all right, V out of t, how would I construct V out of t from this guy? How would I construct V out of t from this guy? Well, V out of t is a periodic waveform, right? So he has a Fourier series as well, right? He's written as a Fourier series. So I can say this guy goes like this. And how would I write out that Fourier series in this case? What was the Fourier series expression, right? Basically says that this periodic waveform is a sum of sine waves. So how can I write this thing out? How would I express this thing? Hopefully somebody knows. So I have e to the what in here? If I write this guy in the complex form of the series, I have e to the what? E to the j what?
And omega t.
and omega naught t, right? And then it has a Fourier series coefficient. What's this Fourier series coefficient?
Alpha.
Basically the multiple, it's yeah, so in this case, if the Fourier series coefficients of the input were alpha n, the Fourier series coefficients of the output basically are h n omega naught times alpha n. So I'm basically saying that the output has the Fourier transform or the Fourier series coefficients of the input times whatever the magnitude of h is at those frequencies. So if I expanded this, whoa, what did I do? Okay, so if I expanded this guy here for a second, okay, let's just do this, you know, coefficient by coefficient. So if I have the n equals 0 term, if I plugged in n equal to 0 into this expression, what would I get? I would get h of 0 times alpha 0 times e to the j 0. What's e to the j 0?
1.
1. So h of 0 times alpha 0 is apparently, according to what I have here, this guy is 2.5. So it's saying I have 2.5 volts in my output. Now let's then take a look at the terms at n equal 1 and n equal to minus 1. So at n equal 1, I have 0.016 times e. So yeah, e to the j omega naught t. And then at this is the n equal 1 term. And then I have 0.016 e to the negative j omega naught t. Right? This is the n equal minus 1 term. And then I can keep going and saying, okay, well, apparently at the n equal 3 term and the n equal minus 3 term, it would appear that I've got some stuff as well. What did I leave out though? I left something out of these n equal 1 and n equal minus 1 terms, right? 0.016 was the magnitude. I also wrote the angle here. So it looks like the angle is, in fact, just to keep it simple, you guys will like it better this way. So I'll say this is 0.016 with an angle of 95 or negative 95.77 degrees times e to the j omega naught t. And this guy is 0.016 times angle 95.77 degrees. Like that. And then I can keep going for the third harmonic. Third plus the minus third plus the fifth plus the minus fifth. I can keep going. What do I know about these two together though? What are they going to give me in the time domain? If I put those together.
A single cosine.
Yeah, and so it would be 2 times 0.016 times cosine of omega naught t plus apparently negative 95.77 degrees. 0.77 degrees. Okay. So 2 times 0.016. This works out to be, I don't know, about 0.032, right? So here's what I did was I went ahead and I created that Fourier transform, right? And this is the way I did it. So the blue waveform here, this was my original input. This was V in of t. And the red here is V out of t. Right? So if I looked at this on the oscilloscope, what it's saying is that the only thing left pretty much is the DC term plus that sine wave at the fundamental frequency. So if now there's other ones there, they're just very, very small. Like the third harmonic is apparently got a very tiny amplitude. Fifth harmonic has an even tinier amplitude. Seventh harmonic, even tinier still, right? So if I wanted to check, so if I go into MATLAB, what I did was I had it tell me what's the peak to peak value. When I had it tell me that, it came out to be about 0.062 volts. All right, and that's pretty close to what I would see here. This guy is 0.032 is the amplitude here. So why would the peak to peak value be about 0.062 volts? Why is the peak to peak value that? So if I calculated that it's a cosine with an amplitude of about 0.032, why would the peak to peak value be about 0.062?
So that's a half power.
Well, because it's peak to peak, right? So if I looked at the peak to peak, if I zoomed in on it, right, the amplitude is this value, right? This would be the 0.032. If I looked at the peak to peak, it's actually, I think I wrote that wrong. It's actually about 0.064, right? It's pretty close to that. Basically, the peak to peak value is what I would see if I look from the top to the bottom, which is twice the amplitude, right? So, I mean, that's the way all this stuff kind of comes together. The thing that you guys need to be able to do, right, is you need to be able to kind of think about, for now, how do I go through this process of determining the Fourier transform of the output and then relating that back to something that exists in the real world? In other words, what we call the time domain. Okay. All right. I think I'm right up on, we're pretty close up on 215. Any questions about that? Basic process. Does that make sense? You guys just afraid to say that it doesn't? Either it painfully makes sense, or you're afraid to say that it doesn't make sense.
It makes sense. It's a lot to take in.
Okay, fair enough. So just out of curiosity, what if I took my h of omega and I were to change the values of L and C, so h of omega kind of expanded outwards? Well, if I expanded it outwards, in other words, if I pulled h of omega out, that was the thing I did in the other case last time, right? Was I said, okay, for a different set of values, my h of omega is pretty constant, right? What would the time domain waveform look like if my h of omega was constant, right? In other words, it was a magnitude of 1. What would V out of t look like? What does V out of t look like in this case?
It would look like the input.
Yep, it would look like the input because you're passing all of the frequencies. All right, that's the idea. All right, so in problem 4, for instance, like you've got 2 different values of the coefficients in the differential equation. In one case, you're doing more filtering than you are in the other case. And so in the one case, the input and the output look a lot more similar. But for the different coefficients, I'm filtering more of the harmonics. And so they look, the input and the output look a lot different because I've filtered out a lot of the harmonics from the waveform. All right, now you're going to apply this concept in the project a bit, and you're actually gonna play with h of omega to get particular outputs. In other words, you're going to try to change h of omega to get the output to behave a certain way. Questions?